Almost every picture of a black hole begins with the same familiar image. Space is shown as a flat sheet covered by a neat grid. At the center, the grid bends downward, becoming steeper and darker until it forms what looks like a bottomless funnel. Somewhere deep inside that funnel sits the black hole, as though the universe has opened a pit beneath itself. It is an effective picture because it turns an invisible idea into something we can recognize. We understand slopes. We understand holes. We understand what it means for an object to fall downward. So when the grid curves into darkness, the meaning appears obvious. The black hole must be below ordinary space, pulling everything toward a deeper level. But imagine placing a spacecraft beside that picture. The pilot approaches the black hole without moving toward the mouth of the funnel. Instead, the spacecraft travels around its side, then continues toward the region that appears to lie underneath it. What should the pilot find there? Another side of the black hole? The narrow end of the funnel? Empty space? Or some hidden destination beneath the universe itself? The picture seems to offer an answer, yet it immediately creates a problem. Turn the entire illustration upside down, and the funnel now points in the opposite direction. Rotate it sideways, and the supposed depth of the black hole points sideways too. Nothing about the black hole has changed. Only the page has moved. That means the downward direction cannot belong to the black hole in the same way that mass, motion, or distance might. It belongs to the way the picture was arranged. Someone had to choose which direction would appear lower on the page. Another person could draw exactly the same idea with the funnel pointing upward, left, or right. The contradiction becomes even clearer if two observers view the same black hole from opposite sides. Each could place the object at the center of a diagram. Each could draw space bending away from their own viewpoint. If both drawings used a downward funnel, their funnels would point in different physical directions. They could not both identify one universal region beneath the black hole. This is the moment when a useful image becomes a trap. It encourages us to treat a drawing of curved space as though it were a landscape seen from outside. Yet the imagined viewer standing outside the grid has no assigned place in the scene. The diagram gives that viewer a viewpoint reality may not provide. Its clarity comes from adding a direction, and that added direction becomes mistaken for part of reality. So the simple question, what lies directly above or below it, is already more difficult than it sounds. The words above and below require a reference. On Earth, the ground and gravity give those words an obvious meaning. In an illustration, the edges of the page do the same. But near a black hole, we cannot assume that either reference still applies. This does not mean direction becomes meaningless. A spacecraft can still move closer or farther away. An observer can still describe one side or another. A real black hole may also possess features that create meaningful directions around it, but those directions must come from the physical object and its surroundings, not from a line drawn downward on paper. The familiar funnel has therefore hidden the real mystery. The question is not what waits at the bottom of the picture. The question is whether a black hole has a bottom at all, whether any side is truly above another, and what an approaching observer would actually encounter after the false vertical direction is removed. To answer that, the funnel must be set aside for a moment. Before asking what lies around, above, below, or inside a black hole, we first have to identify what a black hole physically is. Once the funnel is removed, a black hole becomes harder to picture, but easier to describe accurately. It is not a deep object hanging beneath space. It is not an empty tunnel punched through the universe. And it is not a solid sphere with a dark surface. A black hole is a region of space-time from which nothing can return to the distant universe once it has crossed the region's boundary. That boundary is called the event horizon. The name can make it sound like a visible edge, perhaps a dark shell surrounding whatever lies inside. But the event horizon is not a wall. It is not made of matter, and an approaching object does not collide with it. Light and matter can cross inward without striking any physical surface. What makes the horizon important is not what it is made from, but what becomes possible on either side of it. Outside the horizon, light can still travel along paths that may eventually carry it away. A signal sent from the right place, in the right direction, can still reach the wider universe. At the horizon, that freedom ends. After something crosses inward, none of its future signals can escape back across the boundary and reach a distant observer. The horizon therefore marks a limit in cause and effect. It separates events that can still communicate with the outside universe from events that cannot. This definition also reveals why many familiar black hole pictures can be confusing. Almost everything bright in those pictures is not the black hole itself. The wide, glowing band, often shown circling the darkness, is matter outside the horizon. The narrow beams, sometimes extending in opposite directions, are also external structures. Even the dark central area in a black hole image should not automatically be treated as a photograph of a solid object. The black hole is defined by the hidden region and its boundary. The light around it comes from matter responding to the extreme environment nearby. That matter can make the black hole's presence easier to detect, but it is not required for the black hole to exist. Remove the glowing material, and the event horizon remains. Remove the beams, and the black hole does not lose two physical pieces of itself. An isolated black hole, surrounded by little luminous matter, could be almost invisible against the darkness around it. This distinction matters because the question of what lies above or below a black hole can easily become a question about the wrong object. A bright disk may have an upper face and a lower face. A pair of beams may extend in two opposite directions. But neither one defines the black hole itself. They belong to its surroundings. Before those structures can tell us anything about direction, we have to separate them from the boundary they surround. To keep the terms clear, the event horizon is the boundary. The black hole is the region it encloses. Surrounding gas belongs outside. And the singularity is a prediction about the interior, not a visible dot at the center of an image. The shadow is different again. It is the dark appearance created when light paths are captured or redirected before reaching us. These names describe connected parts of one system, but they are not interchangeable. Mixing them together makes later questions about location much harder to answer. The word horizon also helps us avoid another mistake. On Earth, a horizon is a line beyond which our view is blocked by distance and the shape of the ground. A black hole's event horizon is more serious. It is not merely something we cannot see past because our instruments are too weak. It is a boundary beyond which an outward message cannot return to us. Better telescopes may reveal the environment closer to that boundary, but they cannot receive a signal sent outward from inside it. The size of this boundary depends on the black hole's mass. In the simplest non-rotating description, each mass equal to the Sun corresponds to a horizon radius of roughly 3 kilometers. That does not mean every black hole is only a few kilometers wide. A black hole containing several times the Sun's mass has a larger horizon. A supermassive black hole, containing millions or billions of solar masses, can possess a horizon on a scale comparable to distances found within a planetary system. The contrast is striking. One black hole may enclose its hidden region within a scale familiar from travel between cities. Another may place its horizon across a region so large that an ordinary planetary orbit would no longer feel like an enormous measure. Yet the essential definition remains the same. In each case, the horizon marks the boundary beyond which communication with the distant outside universe is lost. Nothing in that definition requires a downward opening. It describes a region surrounded by a causal boundary, not a pit with a mouth at the top. Nor does it require the glowing structures that often make black holes visually dramatic. Those structures can reveal how matter behaves nearby, but the black hole remains the region from which future signals cannot escape. We have therefore replaced the false funnel with something more precise: a hidden region, an event horizon, and an outside universe that can no longer receive information from anything crossing inward. But this answer creates the next problem. A boundary may surround a region in many possible ways. It could possess a preferred side, an axis, or some other difference between one direction and another. To know whether a black hole can truly have an above or a below, we now have to ask what shape its horizon takes. The event horizon gives us a boundary. Its shape tells us whether one part of that boundary is physically different from another. To see the answer clearly, we have to begin with the simplest black hole that our description allows. Imagine removing everything that might provide an outside sense of orientation. Take away the glowing matter, the surrounding stars, and any beams stretching into the distance. Remove electric charge. Most importantly, remove rotation. What remains is an ideal black hole that is static, uncharged, and non-rotating. This is the kind of black hole described by the Schwarzschild model. The name may sound technical, but the central idea is simple. In this model, the black hole has mass, and that mass affects the spacetime around it. Yet nothing about the black hole points in one angular direction rather than another. It has no spin axis. It has no physical north pole. It has no equatorial plane chosen by its own motion. Its event horizon is spherical. That sphere should not be imagined as a hard black ball. The horizon is still a causal boundary rather than a material shell. Calling it spherical means that the same horizon radius surrounds the center in every direction. If an observer could mark points all around that boundary, no point would be farther from the center merely because it had been placed at the top, bottom, left, or right of a drawing. This property is called spherical symmetry. A familiar ball offers a limited way to understand the word symmetry, even though the event horizon is not made of solid material. On a perfectly uniform ball, rotating the entire object does not reveal a special face. What appeared to be the top can become the side, yet the ball itself remains unchanged. Its shape does not announce that one direction must be treated as superior to another. The horizon radius provides a way to see this equality. Imagine covering the spherical boundary with identical patches. At the same radius, a patch assigned to the top does not gain a different horizon because of its label. Move that label elsewhere, and no measurement tied to the black hole notices. The horizon's radius is defined around the center. It does not grow into a long neck on one side or narrow toward a point below. The direction of a drawing cannot alter that distance. This remains true whether the horizon belongs to a small black hole or a supermassive one. Their scales differ, but increasing mass does not create a preferred side in the non-rotating model. The boundary grows while preserving the symmetry. A larger sphere does not become more upward or downward than a smaller sphere. Size changes the distance involved, not the status of one direction compared with another. This lets us separate two questions that pictures mix together: how geometry changes with distance, and whether that geometry points toward a universal lower region. The same principle is deeper around a non-rotating black hole. Rotate the coordinate system used to describe it, and the physical description stays the same. A scientist may label one direction north and the opposite direction south because labels are useful. Another scientist may choose a different axis. Neither choice changes the strength or structure of the surrounding geometry. The labels organize the map. They do not create new features in the territory. Imagine two identical spacecraft approaching the same black hole from exactly opposite directions. One pilot chooses to call the approach a descent from above. The other, viewing the system from the opposite side, calls the journey a descent from below. If the black hole is truly non-rotating and nothing else breaks the symmetry, both spacecraft face equivalent exterior conditions at matching distances from the horizon. Neither pilot is approaching a rear entrance. Neither has found the underside of the horizon. One route is not closer to a hidden bottom simply because it occupies the lower part of somebody's diagram. The paths are opposite in direction, but the black hole gives us no physical reason to rank one as above and the other as below. We can repeat the experiment from any angle. Place spacecraft around the horizon as if they occupied points across an invisible surrounding sphere. Let all of them begin at the same distance and move inward under equivalent conditions. Their positions may have different names on a coordinate grid, but those angular labels do not identify different kinds of horizon. No spacecraft finds the mouth of a pit while another finds its outer wall. Each approaches the same causal boundary from a different radial direction. The word radial is important. It describes movement toward or away from a center. Inward does have physical meaning here. A spacecraft can reduce its distance from the horizon, just as it can move farther away. But inward is not the same as downward. Inward can point from every surrounding direction toward the black hole. If observers form a sphere around it, each observer's inward direction points differently in the wider space, yet all point toward the same central region. This is why an ideal black hole cannot be understood as a hole cut into a floor. A hole in a floor has a preferred entrance because the floor already supplies an upper side and a lower side. Objects begin above it and fall through it. The Schwarzschild black hole comes with no such floor. Its horizon surrounds the hidden region instead of opening toward it from one privileged direction. The first answer to our central question is therefore surprisingly clean. For a non-rotating black hole considered by itself, there is no natural top or bottom. There is no special north or south unless an observer chooses labels for convenience. Nothing intrinsic to the horizon marks one side as the upper side or another as the lower side. Every radial approach is equivalent to any other after the entire arrangement is rotated. But this clean answer depends on the simplicity of the model. A real environment can provide reference points. Nearby matter can orbit in a plane. Distant objects can help observers agree on an orientation. More importantly, a black hole can rotate, and rotation can give the system a genuine axis. Those complications will eventually allow us to discuss poles and an equator without returning to an absolute universal up or down. Before adding them, however, one contradiction remains. If the simplest black hole is surrounded by a spherical horizon, why has the downward funnel become the image almost everyone recognizes? The sphere and the funnel appear to tell completely different stories. One treats every direction equally. The other seems to select one direction and stretch space into a deep pit. Both images cannot be literal descriptions of the same geometry. To understand what the funnel is actually showing, we have to discover where its downward direction came from. The conflict between the sphere and the funnel begins with a problem of representation. Curved spacetime is not something we can place on a page in its complete form. A page has only two visible dimensions, while the physical situation contains more. To make part of that geometry easier to study, a diagram must leave some information out and turn other information into a shape we can see. The familiar funnel is one result of that process. It is commonly called an embedding diagram. The purpose of such a diagram is not to show a black hole as it would look from a hidden viewing platform outside the universe. Its purpose is to take a reduced part of the geometry and display certain relationships through an added visual direction. Begin by imagining the space around a non-rotating black hole at one chosen moment. Even that spatial picture is too large to show directly on an ordinary sheet, so the representation simplifies it. Instead of trying to display every possible direction, it selects a thinner slice through the surrounding space. Then it reduces that slice again until the remaining surface can be drawn. The result no longer contains the full physical situation. It is a carefully limited model. To make the curvature within that reduced surface visible, the diagram places the surface inside a separate, familiar space. The grid is then shown bending along an extra display direction. That bending produces the funnel. The crucial point is that this added vertical direction was introduced by the representation. It allows our eyes to see relationships that would otherwise be difficult to express on a flat page. It does not identify another route within the original space around the black hole. The diagram needs that extra direction in much the same way that a chart may use height to display a value. The height carries information, but it is not automatically a physical altitude in the system being described. This explains why turning the diagram changes its apparent down without changing the black hole. The direction was never selected by the horizon. It was selected by whoever arranged the display. The grid could bend upward and communicate the same geometric relationship. It could point left or right. Viewers are accustomed to reading gravity as downward, so the downward version feels natural, but familiarity does not make that direction part of the represented spacetime. A map offers a restrained comparison. Earth is curved, yet a flat map can represent places across its surface. Every flat projection distorts something because a curved surface cannot be transferred to a plane without compromise. One map may preserve some shapes while stretching areas or distances. The distortion does not make the map worthless. It means the reader must know which features the map is designed to preserve and which features should not be taken literally. The comparison shows why changing the representation does not change the object. A globe, a world map, and a polar map can depict Earth while arranging the surface differently. Their edges and orientations belong to their formats. In the same way, changing how a curved spatial slice is displayed can change the shape or direction of the funnel without changing the black hole. Physical conclusions must come from relationships preserved by the model, not from the display's orientation. The funnel has a similar boundary. It can help communicate that the spatial geometry around a concentrated mass does not behave like an ordinary flat grid. Distances and radial relationships do not follow the simple expectations we develop in nearly flat surroundings. The increasingly steep appearance can represent how difficult those relationships are to place within the chosen display space as the horizon is approached. But the steepness is not a hillside. An astronaut near the black hole would not see a grid sloping toward a mouth. The spacecraft would not need to point its nose downward to approach the horizon. It could not circle beneath the sheet and locate the pointed end of the funnel. That region exists only in the space used to display the reduced geometry. It is not a hidden chamber attached to the physical universe. This also means the narrow end should not be identified with a tunnel leading directly to the singularity. The diagram is built from a selected spatial description outside the horizon. Its shape cannot serve as a complete map of the interior, and its visual depth should not be read as the distance an infalling observer travels toward a bottom. The picture has already removed dimensions and added a display direction. Asking it to reveal the full interior gives it a task it was never designed to perform. Consider again the imagined spacecraft that tried to fly underneath the funnel. We can now say exactly why that journey fails. The pilot was being asked to move along the diagram's added direction, but that direction is not among the available routes represented within the original physical space. It is a viewpoint tool, not a navigation coordinate. There is no command the pilot can enter that means fly out of space-time and descend through the visual depth of an embedding diagram. If the spacecraft instead travels around the black hole within real space, it remains in the exterior geometry described by the model. It can approach from one radial direction, pass around to another, or move farther away. None of those paths brings it behind the page. The supposed underside disappears as soon as we stop confusing the display space with the physical space being displayed. The funnel, therefore, lies only when we ask it a literal question. Used carefully, it can reveal that geometry is not flat and that radial relationships change near the horizon. Used carelessly, it suggests a floor, a slope, an absolute downward direction, and a bottom located somewhere outside ordinary space. Those additions come from the visual method, not from the black hole. This distinction protects us from making the opposite mistake as well. We should not conclude that every picture of curved space is meaningless, or that geometry cannot be understood. Scientific models often become useful by selecting only the features needed for a particular question. Their power depends on knowing their limits. The embedding diagram answers a question about a reduced geometry. It does not answer where a spacecraft would find the physical underside of a black hole. The mystery introduced by the opening image is now resolved. Nothing waits beneath the funnel because the funnel is not hanging inside the universe. Its downward axis belongs to the diagram. The actual event horizon surrounds a region in physical spacetime, while the apparent depth exists only to help us view selected geometric relationships. Yet removing this false direction does not leave an observer without orientation. A spacecraft can still measure whether it is moving inward or outward. It can establish directions using instruments, motion, and surrounding objects. Some black holes can also possess physical features that distinguish one axis from another. The next question is therefore no longer what lies below the picture. It is how real directions are constructed near a black hole once the picture's invented vertical has been removed. Once the diagram's false vertical is removed, the space around a black hole does not become directionless. An observer can still move, turn, measure, and compare one path with another. What disappears is only the claim that the universe supplies one permanent direction called up and an opposite direction called down. Real orientation must be built from physical relationships. The clearest relationship is radial distance. Outside a black hole, an observer can describe movement as inward when the distance from the horizon decreases, or outward when that distance increases. These are meaningful distinctions because instruments and signals can reveal whether the observer is approaching the boundary or moving away from it. Yet inward is not another name for downward. Around a spherical horizon, Inward points toward the black hole from every side. If many spacecraft surround the horizon, each craft has its own inward direction. Their arrows point differently when compared across the wider space. But every arrow leads toward a smaller radial distance. No single arrow has to point toward the lower edge of a universal picture. Outward behaves the same way in reverse. Each spacecraft can move away from the horizon, but the outward directions spread across the surrounding space. One pilot's outward path may point opposite to another pilot's. Both descriptions remain correct because outward refers to increasing distance from the black hole, not movement toward one fixed cosmic ceiling. Movement can also be tangential. Instead of approaching or retreating, a spacecraft can travel around the black hole, changing its angular position while remaining at roughly the same radial distance for part of its path. This gives the pilot a practical distinction between moving toward the horizon, away from it, or sideways around it. None requires the artificial depth of the funnel. To use these directions, an observer needs a local frame of reference. Local means the frame is constructed in the observer's immediate surroundings rather than imposed on the entire universe. A spacecraft can treat its forward direction as the direction its nose points. Its floor and ceiling can define a temporary down and up for the crew. Instruments can track changes in motion, and light signals can help compare the craft's position with nearby objects. A gyroscope gives another useful reference. Once set in a particular orientation, it helps the spacecraft notice when the craft turns relative to that carried direction. The crew can use several such measurements to organize their surroundings into practical axes. They can say that one object lies above the cabin, another lies ahead, and the black hole lies inward. Those statements have clear meaning inside the chosen frame. Light signals make the frame more than a set of names. By sending pulses toward markers and measuring what returns, observers can compare directions and changes in separation. Different observers may organize the results with different coordinates, but they can agree about whether their spacecraft moved closer together or farther apart. Measurement gives the description a physical core. The coordinate system packages that information. It does not manufacture the events measured. But turning the spacecraft changes the cabins up and down. If the pilot rolls the craft halfway around, the former ceiling becomes the floor from the crew's new orientation. The black hole does not rotate with those labels. This is the difference between a useful local vertical and an absolute vertical built into space itself. Nearby objects can provide a wider reference. The crew might compare its direction with distant stars, the motion of surrounding material, or an orbital plane. If several observers agree to use the same objects, they can share a common coordinate system. They may decide that one side of the system is north and the opposite side is south. This agreement makes communication easier, but the names still come from the chosen reference. Coordinates are valuable because they allow observers to record locations and compare measurements. A label does not need to be absolute to be useful. A city map can assign north to the top of a page, and everyone using that map can follow the same direction. Turning the paper does not move the city. In the same way, turning a coordinate diagram does not rearrange the black hole. The important question is whether changing the labels changes a physical result. Around the ideal non-rotating black hole, choosing a different angular axis does not uncover a new feature of the horizon. A point labeled north can be relabeled east or south without altering the geometry there. The coordinate name changes. The physical relationship does not. This does not make the relationship imaginary. Radial distance remains measurable. Motion relative to nearby objects remains observable. The direction carried by a gyroscope can remain stable enough to guide local comparisons. What is absent is a single angular axis selected by the non-rotating black hole itself. That distinction allows us to sort directional statements into two groups. Some directions describe measurable relationships, closer to the horizon, farther from it, along a path around it, or aligned with a chosen object. Other directions are merely labels placed on equivalent parts of a symmetric system. Confusing these groups makes an arbitrary North Pole seem like a special physical region. Suppose two research teams approach the same non-rotating black hole from different sides. Each team constructs a local frame. Each calls the direction away from the cabin floor up. Each chooses familiar stars to label the larger surroundings. Their maps may look different, yet the teams can translate between them by identifying shared objects and motions. Neither map has to be declared the universe's one correct orientation. The situation is similar to meeting travelers who use different ways of describing the same route. Once their reference points are known, their statements can be compared. The disagreement may concern labels rather than physical events. Near the black hole, the task is to ask what each direction is measured relative to before deciding what the statement means. This is why the title's words can become scientifically useful only after a reference is supplied. Above what? Below which plane? Aligned with which axis? Moving away from which center? Without those details, above and below describe the orientation of a speaker or image more clearly than they describe the black hole. Several physical features could supply such details. Surrounding matter may travel in a shared plane. A magnetic field may have an organized direction. A spacecraft may choose an axis using distant objects. These references can make one side of a system meaningfully different from another for a particular measurement, even though none creates a universal vertical. The most important reference can come from the black hole itself. The non-rotating model had mass, but no angular momentum. It remained unchanged when its angular coordinates were rotated. If the black hole carries angular momentum, however, it is no longer enough to describe only how much mass it has. Its rotation also has an orientation. An orientation of rotation selects an axis. The two opposite directions along that axis can be called poles, while directions around the middle can define an equatorial region. These are not labels attached to equivalent points for convenience. They are tied to a measurable physical property of the rotating system. Even then, the axis will not become an absolute up for the universe. Another black hole could spin along a completely different orientation. An observer could still choose either pole to call north. But pole and equator would no longer be interchangeable in every physical description. Rotation would have broken the perfect angular equality of the simpler model. We now have the directional vocabulary needed to move beyond the ideal spherical case. Inward and outward describe radial change. Tangential motion carries an observer around the horizon. Local frames organize immediate experience. Shared objects and planes allow different observers to compare maps. And angular momentum can give the black hole a physical axis of its own. The question is no longer whether direction survives near a black hole. It does. The question is what space-time becomes when the black hole itself begins to spin. Angular momentum changes the black hole from a system with no preferred angular direction into one with a physical axis. The appropriate description is no longer the static Schwarzschild model. A rotating black hole is described by the Kerr model, and its geometry carries the effect of that rotation throughout the surrounding spacetime. The difference begins with symmetry. The non-rotating black hole remained physically unchanged no matter how its angular coordinates were turned. A rotating black hole does not preserve that complete spherical equality. Its spin selects an axis running through the central region. Rotation takes place around that axis, giving the system two opposite polar directions and an equatorial region around the middle. This is called axial symmetry. Turn the description around the spin axis, and the system can remain equivalent. But tilt the axis so that a pole is exchanged with the equator, and the physical arrangement is no longer the same. Pole and equator now refer to different relationships with the black hole's angular momentum. A spinning wheel offers a limited comparison. Its axle marks two opposite directions, while points around its rim circle that axle. If the wheel is turned, the orientation of the rotating system changes. The black hole's axis plays an organizing role, but it is not a rod passing through a material object. It is the direction defined by the black hole's angular momentum. Observers can identify it through physical effects, even though no line runs through space. This makes the distinction measurable rather than decorative. A coordinate grid placed on the non-rotating horizon could choose any axis without changing the system. For the Kerr black hole, a grid aligned with the spin captures a relationship already present in the geometry. Choosing another axis remains possible, but it will not erase the role of the rotation axis. The two poles do not arrive with permanent names. An observer may call one north and the other south, while another observer could reverse those labels. What matters is not which pole receives which name. What matters is that both lie along the spin axis, while the equatorial directions lie around it. The axis is physical, even though its naming remains conventional. This gives above and below a qualified meaning. If observers agree that one spin pole defines above, then the opposite pole defines below. Their choice does not establish an up and down for the whole universe. It establishes an orientation relative to this rotating black hole. Another black hole can spin along a different axis, making its relative above point somewhere else entirely. Rotation also changes the shape associated with the horizon. Instead of the perfect spherical symmetry of the non-rotating case, the rotating horizon is oblate. In simple terms, the geometry is flattened in relation to the spin axis rather than remaining identical under every possible rotation. This should not be pictured as a rubber ball spinning so quickly that its material surface bulges. The event horizon is still not a solid object. Its shape belongs to the geometry of the causal boundary in the rotating spacetime. The black hole's angular momentum alters that geometry. No material crust is being stretched around the middle. The influence of rotation does not stop at the horizon. Spacetime around the black hole is affected as well. The Kerr geometry includes an effect known as frame dragging. The phrase describes how the rotating black hole carries nearby spacetime around with its motion. An ordinary picture of rotation often places a spinning object inside a passive background. The object turns, while the space around it remains an unmoving stage. Near a rotating black hole, that separation is inadequate. The geometry that determines possible motion is itself twisted around the spin axis. An observer trying to maintain an orientation relative to the distant universe must account for this dragging. Far from the black hole, the effect is weaker. Closer to it, rotation increasingly shapes the paths available to matter and light. This does not mean every nearby object simply becomes attached to the horizon. It means that the distinction between the rotating object and an unaffected surrounding space no longer captures the physical situation. The rotation is written into the spacetime through which objects move. Outside the event horizon lies a region called the Ergosphere. It appears only in the rotating description and has a different boundary from the horizon itself. Entering the Ergosphere does not yet mean that escape to the distant universe has become impossible. The region remains outside the black hole's one-way causal boundary. Yet an observer in the ergosphere cannot remain stationary relative to the distant universe. Frame dragging has become strong enough that every possible physical observer there must move around the black hole in the direction of its rotation. The observer may still control parts of that motion and may still escape under suitable conditions, but simply hovering without sharing any of the rotation is no longer an available state. This distinction matters. The event horizon decides whether future signals can return to the outside universe. The ergosphere marks a surrounding region where rotation controls the possible motion in a different way. Confusing the two would make it seem that forced co-rotation and permanent causal capture begin at the same boundary. They do not. The ergosphere also reveals that the black hole's rotation is not merely a label. Rotational energy can interact with processes outside the horizon. Fields and matter in the surrounding environment can respond to the rotating geometry. This creates the conditions under which energy associated with the spin may influence visible activity around an astrophysical black hole. But geometry alone does not supply the glowing material. An isolated Kerr black hole can possess angular momentum, a spin axis, frame dragging, and an ergosphere without displaying a bright disk. It does not automatically produce two luminous beams merely because it has two poles. Visible structures require matter and fields in the surrounding environment. This prevents us from answering the title too quickly. Directly along the two spin directions, there may be little luminous material at all. The meaningful result at this stage is geometric. The rotating black hole has polar directions that differ from its equatorial region. What physically occupies those regions depends on what is falling toward the black hole and how that material behaves. Imagine approaching such a system from several angles. A spacecraft traveling toward a pole follows a direction aligned with the angular momentum. A spacecraft approaching near the equatorial region enters along a direction perpendicular to that axis. These paths can no longer be exchanged by any rotation while leaving the entire physical description unchanged. The black hole's spin distinguishes them. Neither route, however, leads to a universal top or bottom. The polar spacecraft is not above all of reality. It is above only according to an agreed orientation tied to this black hole's axis. The equatorial spacecraft is not approaching from the side of a cosmic floor. It is approaching through a region defined relative to the same rotation. We can now give the title its first answer for a realistic rotating case. Above and below can refer to the two opposite directions along the spin axis. Between them lies the equatorial region. These distinctions are physical because angular momentum selects the axis, even though the choice of which pole to call above remains ours. The result is more precise than the old funnel image. Rotation does not create a pit pointing downward. It creates an axis, twists the surrounding spacetime, changes the horizon geometry, and produces an ergosphere outside the event horizon. Direction emerges from the black hole's motion, not from the orientation of a page. Still, a purely geometric axis would be difficult to see. Real black holes become visible through the behavior of surrounding matter. Gas arriving with its own motion does not usually fall straight inward from every direction. It circles, collides, heats, and reorganizes around the rotating system. To discover what may physically occupy the equatorial region, we have to follow that matter as it collects around the black hole. Matter approaching a rotating black hole rarely begins with a perfectly straight path toward the horizon. Gas in space is already moving. Different streams arrive from different directions, carrying sideways motion as well as inward motion. That sideways motion gives the material angular momentum, making a direct plunge difficult during its first approach. Instead of falling immediately through the horizon, much of the gas passes around the black hole. Gravity bends its path inward, but angular momentum keeps it circling. The result is not a stable collection of separate particles moving forever without interaction. The gas meets other gas. Streams cross, collide, compress, and exchange energy. Their motions begin to reorganize into a shared rotating flow. As those interactions continue, the material often settles toward a common plane. Motion that carries gas far above or below that plane can be reduced through collisions and energy loss, while rotation around the central axis remains. The flow becomes concentrated around an equatorial region, defined by the system's angular momentum. This surrounding structure is called an accretion disk, although the word disk can suggest something more neat and solid than the real flow. It is not a rigid plate. It is moving material, often in the form of hot plasma, orbiting outside the event horizon. Different parts of the flow can move at different rates, and its form can change with the conditions supplying the black hole. The disk does not simply remain at one distance. Some material gradually moves inward and may eventually cross the horizon. For that to happen, however, the material must lose enough angular momentum. An orbiting parcel cannot move much closer while keeping all the sideways motion that holds it in its present path. Angular momentum, therefore, has to be redistributed. Material moving inward transfers part of its angular momentum to material farther out. The outer material can then move outward or carry that angular momentum away, while the inner material becomes able to approach the black hole. Accretion is not merely matter being pulled down. It is a continuing exchange that allows some matter to spiral inward as other parts absorb what it gives up. The inward journey is therefore gradual for much of the material. A parcel of gas may circle the black hole many times while exchanging energy and angular momentum with the surrounding flow. Its path is a spiral rather than a vertical fall. Each change in orbit brings it into a different relationship with neighboring plasma, and those interactions decide whether it moves closer, moves outward, or remains in the flow longer. The disk is a process of movement and exchange, not a waiting room filled with matter at rest. Different regions of the flow also perform different roles. Material farther out can act as a reservoir receiving angular momentum, while inner material reaches conditions where continued orbit becomes increasingly difficult. Yet there is no single visible line that always separates safe orbit from immediate capture in every real disk. The observed brightness may end before the horizon, and faint material may still continue where the image appears dark. What the telescope records depends on emitted light, while the causal boundary is defined by which future paths can escape. Keeping those ideas separate prevents brightness from becoming a false map of the horizon. The flow is made more complex by turbulence and magnetic activity. They help connect neighboring regions and move angular momentum through the plasma. This should not be pictured as ordinary friction between a solid disk and a surface beneath it. There is no supporting surface. The interactions occur within the moving plasma itself, and the entire structure remains suspended in orbital motion around the black hole. As material changes orbit and moves inward, energy is released within the flow. Collisions, compression, and turbulent motion help turn organized orbital energy into heat. The plasma can become extremely luminous, making the environment around the black hole far easier to detect than the horizon itself. This is why familiar black hole images often show a glowing band around a central darkness. The light comes from matter outside the event horizon. It is evidence of an active surrounding environment, not light emitted by a solid black surface. The black hole remains defined by the hidden region and causal boundary established earlier. The disk reveals what matter is doing before it crosses that boundary. The distinction becomes especially important near the inner part of the flow. A bright inner edge in an illustration should not automatically be identified as the event horizon. The location and appearance of the emitting material depend on its motion, temperature, density, magnetic conditions, and on how its light travels to the observer. The horizon itself does not become a glowing rim merely because the nearby plasma is bright. An approaching spacecraft would therefore encounter a changing environment rather than a clean boundary drawn in light. Depending on the system, the region near the equator could contain thin luminous material, a thicker flow, faint gas, or intense plasma. The disk may be uneven, turbulent, and variable. It may also be tilted relative to the black hole's spin rather than forming a perfectly aligned ring. The word equatorial must be used carefully for that reason. The black hole's rotation defines its own equatorial region. Incoming matter carries angular momentum that may begin with another orientation. The flow can respond to the rotating geometry, but the surrounding material does not have to arrive already arranged in a perfectly flat plane matching the horizon's equator. This creates a system with more than one source of orientation. The black hole has a spin axis. The incoming material has its own overall rotation. Magnetic fields within the plasma can also develop organized directions. Their interactions determine the changing shape of the accretion environment. A simple drawing of one thin, flawless disk captures only one possible arrangement. Some accretion flows are bright enough to dominate everything we see near the black hole. Others are faint because relatively little matter is available or because the flow does not radiate energy in the same way. A black hole may pass through different levels of activity as its supply changes. The geometry of the horizon can remain while the visible environment grows brighter, becomes dimmer, or almost disappears. This variability proves again that the disk is not part of the black hole in the same sense as the event horizon. If the supply of gas decreases, the disk can fade. The horizon does not switch off. If new matter arrives with a different orientation, the flow can change. The black hole's mass and spin may evolve through accretion, but the immediate pattern of glowing matter is still an external, changing structure. We can now answer one part of the original location question more physically. Near the middle region around an active rotating black hole, an observer may find orbiting plasma arranged into an accretion flow. The observer does not find a solid sidewall of the black hole, nor does the observer find the edge of a hole cut into space. The material belongs to the environment outside the causal boundary. That environment can be dangerous and luminous, but its dramatic appearance should arise from its actual mechanisms. Gas carries angular momentum. Interactions redistribute that angular momentum. Some material moves inward. Energy is converted into heat. The hot plasma emits light. Every part of the explanation follows from matter trying to approach the black hole while still carrying motion around it. The result also helps make the black hole's orientation visible. A disk supplies a plane that observers can identify. Once that plane is established, they can describe directions above it, below it, and along its surface. These directions remain relative to the physical system, but they are no longer arbitrary marks placed on an empty coordinate grid. Still, The disk answers only the equatorial part of the mystery. It tells us what can collect around the middle, not what may extend along the spin axis. In some active systems, the most enormous structures are not confined to the disk at all. Narrow outflows travel away from the central region in two opposite polar directions. The same environment that feeds matter inward can help send energy and plasma outward. To understand what may genuinely lie above and below the rotating black hole, we now have to follow those polar beams. The accretion flow carries more than hot matter around the black hole. It also carries magnetic fields. As the plasma moves, twists, and spirals inward, those fields can become organized around the rotating system. Under suitable conditions, the result is not only inward accretion, but also a pair of narrow outflows directed away from the central region. These outflows are relativistic jets. They are found in some active black hole systems and can travel along two opposite directions roughly aligned with the black hole's spin axis. If observers choose one pole as above and the other as below, the jets may become the most striking structures occupying both regions. This is a far more physical answer than the imagined funnel. The beams do not point along an artificial direction added to a diagram. Their orientation can be compared with the rotation and surrounding flow of the real system. They reveal that the polar directions can differ dramatically from the equatorial environment. Around the equator, much of the visible matter circles within an accretion flow. Along the poles, the environment may provide clearer routes for an outflow. Organized magnetic fields can guide plasma and electromagnetic energy away from the central region, helping a broad, turbulent environment form a narrow beam. The complete microscopic story is still an active scientific problem. The detailed behavior depends on the plasma, the magnetic field, the accretion state, and the rotation of the black hole. It would be misleading to reduce every jet to one perfectly settled sequence. Yet the broad picture is well established. Magnetized accretion and black hole spin can work together to power and shape polar outflows. One important part of that picture involves rotational energy. A spinning black hole changes the surrounding spacetime and produces the ergosphere described earlier. Magnetic fields connected with the surrounding plasma can interact with that rotating environment. Under the right conditions, energy associated with the black hole's spin can be transferred into an outward electromagnetic flow that helps power a jet. This does not require matter to climb back out from inside the horizon. The launching region lies outside the event horizon, within the surrounding magnetized environment. Plasma can be accelerated outward before it crosses the one-way boundary. Energy can be carried away through processes operating where communication with the exterior remains possible. That distinction is essential. A jet is not a leak in the black hole. It is not a beam fired from the Singularity. It does not prove that material can enter through the horizon and later escape along a polar tunnel. Once an event lies inside the horizon, it cannot send a future signal back to the distant outside universe, through the jet or by any other classical outward route. The jet, instead, shows how much activity can occur immediately outside the black hole. Matter may be spiraling inward near the equator, while other plasma and energy are directed outward along the axis. Inflow and outflow become connected parts of one active system without violating the horizon's causal boundary. The two opposite polar directions explain why jets often appear as a pair. One extends along one side of the spin axis, while the other extends in the opposite direction. They may be called the approaching and receding jets, depending on their motion relative to an observer. Their observed brightness may differ, even when both belong to the same underlying bipolar structure. The pair need not look perfectly balanced. The surrounding environment can differ on the two sides. The supply of plasma can change. The direction of the jet may shift, and one side may be harder to detect. The existence of two polar directions therefore does not guarantee a flawless mirror image in every observation. Nor does a spin axis guarantee any visible jet at all. A rotating black hole may lack the required supply of matter or the magnetic arrangement needed to power a strong outflow. A jet may weaken, become intermittent, or disappear as the accretion environment changes. The spin axis remains a property of the black hole, even when no bright beam marks it. This separates geometry from activity. The black hole provides a rotating spacetime with a physical axis. The surrounding matter and magnetic fields determine whether that axis becomes visible through a jet. The axis can persist while the beam changes, just as the event horizon persists while the accretion disk brightens or fades. When powerful jets do form, their scale can be astonishing. The central engine operates near a compact horizon scale region, yet the outflow can remain organized across distances vastly larger than the black hole itself. A structure born near the horizon can extend through its host environment and influence regions far beyond the accretion flow. Maintaining narrow form requires organization. The outflow begins where plasma, rotation, and magnetic fields interact, but it does not spread equally. Magnetic structure can help keep energy and matter concentrated along the axis. The word jet describes this focused geometry as much as the speed. That focus does not turn the polar axis into a pipe built into the black hole. There is no nozzle attached to the horizon. The channel is produced by conditions in external plasma and fields. As those conditions evolve, the jet can change its width, direction, strength, and stability. What appears to be one permanent beam is a physical process that must be maintained. This provides another clear guardrail for the title. Finding a jet above a black hole means finding an outflow aligned with a chosen pole of an active system. It does not mean finding the upper end of the black hole. The beam belongs to the environment shaped by the black hole, just as the accretion disk does. The contrast changes the meaning of above and below. Close to the black hole, those words refer to opposite polar directions relative to the spin. Farther out, the jets can carry that orientation across enormous distances. The black hole has not created an absolute vertical for space, but its rotation has organized a real axis that can remain visible far beyond the central region. Imagine approaching an active system from above one pole. The spacecraft may face an outflow traveling outward along its route. Approaching from the equatorial direction would lead toward the orbiting plasma instead. The two journeys differ because the system's rotation, matter, and magnetic fields have made pole and equator physically distinct. Approaching from the opposite pole may reveal the second outflow. Calling one route above and the other below is still a choice made relative to the spin axis. But unlike the upper and lower edges of the funnel drawing, these routes correspond to measurable structures in the surrounding universe. We can now give the title its strongest visible answer. Directly above and below some active rotating black holes lie opposing relativistic jets. Around the middle may lie an accretion flow. These structures make the relative poles and equator observable, while the horizon itself remains a causal boundary rather than a downward opening. The answer must remain conditional. A quiet black hole may have no luminous disk and no visible jets. Another may show a disk, but only weak outflow. The exact environment changes, and no one image describes every black hole. Jets tell us what can occupy the polar regions, not what must always be there. Even when both disk and jets are present, another problem remains. We observe them through light that travels across strongly curved space-time. The apparent position of that light may not provide a simple map of where it began. Material physically behind or below the black hole can sometimes appear somewhere else around the central darkness. We have identified the real structures. Now we have to ask whether a black hole image places them where they actually are. Identifying the disk and jets gives us real structures, but seeing them does not mean seeing a simple map of their positions. Every image is made from light that reached the observer. Near a black hole, the path followed by that light can be so strongly curved that the image places familiar structures in unfamiliar locations. Far from a powerful gravitational field, light often appears to travel along a straight path. This expectation works well enough for ordinary experience that we use the direction of arriving light to judge where an object is. Trace the ray backward, and we expect to find the source along the same straight line. Near a black hole, that method fails. Light follows the geometry of spacetime. When spacetime is strongly curved, the route taken by light is curved as well. A photon emitted in one direction can swing around the black hole before continuing toward a distant observer. The observer sees the light arriving from the final part of that path, not from a straight line connecting the image to the original source. Consider light emitted by matter on the far side of an accretion disk. In ordinary flat geometry, the black hole might appear to block that material from view, but some of the light can travel above or below the central region, curve around it, and reach the observer. The far side becomes visible around the edge of the central darkness. The same effect can reveal the underside of the disk. Light that begins below the equatorial plane can bend upward around the black hole before traveling outward. In the resulting image, that light may appear above the shadow. The upper part of the image can therefore contain information from material that was physically behind or below the black hole. This does not mean the matter itself has moved above the hole. The plasma remains in its part of the accretion flow. What changed was the route taken by its light. The image records where the light appears to arrive from after its journey through curved spacetime, not a direct overhead diagram of where the emitting material sits. The disk can consequently seem to wrap around the central darkness. Light from the near side contributes one part of the image. Light from the far side is lifted into view by gravitational bending. Light from below may appear along an upper arc, while other paths can create corresponding features elsewhere. A structure that is physically concentrated around an equatorial region can appear to surround the shadow. Viewing angle adds another layer. An observer, looking along the spin axis, receives light along different routes from an observer looking across the disk's edge. The system can remain the same while its image changes because different paths connect the plasma to each observer. This is why an image cannot define absolute above or below. Its top and bottom depend on where the observer is placed and how the picture is oriented. Motion within the disk can change brightness across the image. Material on different sides moves differently relative to the observer, so the ring need not appear evenly bright. This asymmetry does not mean one side of the horizon is larger or that the black hole has acquired a solid illuminated edge. It belongs to the combined effects of moving plasma and the paths by which its light arrives. Jets provide a contrast. Their large-scale direction can help identify the polar axis, while the disk supplies an equatorial reference. Yet close to the central region, light from both structures can still be bent before reaching us. Physical orientation must therefore be inferred from the whole system, not read from one pixel or apparent arc. This creates a second trap for the words above and below. Earlier, the funnel gave the diagram an artificial vertical direction. Now, a realistic image can place light from below into an apparently upper position. The first confusion came from how geometry was represented. The second comes from how information travels through that geometry. Not every light path bends by the same amount. Some rays pass relatively far from the black hole and are deflected only modestly. Others travel much closer and turn through larger angles. A ray can curve around much of the black hole before escaping. The closer its path comes to certain critical conditions, the longer it can remain near the central region before finally reaching the observer or falling inward. For the ideal non-rotating black hole, an important scale is the photon sphere. It lies at a radius 1.5 times the horizon radius. At this scale, light can follow circular paths around the black hole in the mathematical description. These paths are unstable. They are not safe tracks where a photon can remain protected from every disturbance. A tiny change can send the light outward or cause it to fall inward. The photon sphere therefore marks a critical structure in the geometry, rather than a durable shell made from stored light. Light that approaches this critical region can circle partway around the black hole, or even complete additional turns, before escaping. Those longer routes allow an observer to receive repeated, increasingly compressed views of emitting material. Each additional path carries information that has traveled around the black hole in a different way. The resulting features are sometimes discussed as higher-order images. They can be narrow and difficult to separate, but their meaning is striking. The same physical region may contribute light to more than one apparent location because different rays follow different numbers of turns before reaching the observer. Several terms must remain separate here. The photon sphere is a geometric scale in the ideal spherical case associated with unstable circular light paths. A photon ring refers to a narrow image feature produced by light that traveled near those critical paths. An observed emission ring can be broader and shaped by the distribution and motion of glowing plasma, as well as by lensing. None of these is identical to the event horizon. The horizon is the causal boundary beyond which outward signals cannot escape. The photon sphere lies outside it. A bright ring belongs to the appearance of light reaching an observer. Treating the ring as a solid surface would combine three different ideas: where light is emitted, how it travels, and where escape becomes impossible. The central dark region in a modeled image also requires care. It is commonly called the black hole's shadow. The shadow is larger in appearance than the horizon itself because it is shaped by the light paths that are captured rather than reaching the observer. It is not a transparent window through which the interior or singularity becomes visible. An observer looking at such an image is therefore seeing a map of possible light journeys. Bright regions identify paths that delivered radiation from surrounding plasma. Dark regions identify directions from which less light reached the observer, including paths captured by the black hole. The image contains evidence about the geometry, but it does not place every source where ordinary vision expects. Computer models can follow many such light paths and calculate how a disk might appear from different viewing angles. These ray-traced simulations are valuable because they connect a physical model of the plasma and spacetime to a predicted image. They show why the far side rises into view, why the underside can appear above, and why a ring can surround a central shadow. But a simulation remains a prediction built from assumptions. It can demonstrate what a particular model would look like if its geometry and emitting material were arranged in the chosen way. It cannot by itself establish that a real object in the sky has exactly those properties. The distinction between prediction and observation is the next necessary step. General relativity tells us what scale the strongly lensed region should have for a black hole of a given mass. Accretion models tell us how nearby plasma might supply the light. A telescope must then determine whether nature produces a horizon-scale structure consistent with that combined picture. We now understand why below can appear above and why the disk can seem to wrap around darkness. The question is whether these curved light predictions have survived contact with the sky. To answer that, we need to examine what an Earth-sized telescope actually measured around two very different black holes. Testing the predicted ring and shadow required a telescope capable of resolving an almost unimaginably small region of the sky. No single ordinary dish was large enough to perform that task. The solution was to connect observatories across Earth and make their separated measurements work together as parts of one virtual telescope. This global network became the Event Horizon Telescope. It observed at millimeter wavelengths, collecting signals from stations separated by great distances. The method is called Very Long Baseline Interferometry. Its underlying purpose can be described simply. The wider the separation between coordinated observatories, the finer the detail their combined data can recover. The network did not operate like an ordinary camera, taking one instant photograph through a single lens. Each site recorded part of the incoming signal, along with precise timing information. Those records were later combined and processed to reconstruct the horizon-scale emission that best matched the measurements. This distinction matters because the image is the result of measurement and reconstruction. The observatories captured radio signals. Researchers then used those data to recover a reliable image structure. Finally, the structure was compared with physical models to determine what it implied about the object producing the light. Confidence in the reconstruction required more than producing one picture. The recorded signals constrained which image structures could match the data. When different reconstruction approaches recovered the pattern, the ring and shadow became harder to dismiss as products of one method. Details could vary in a changing source, but the characteristic scale remained the key comparison. This is why the measured diameter carries weight. A ring alone could arise from different arrangements of emitting material. Its size relative to the estimated mass tests whether light has been organized on the scale predicted near a black hole. Agreement does not remove every modeling assumption, but it ties the image to a quantitative expectation rather than resemblance alone. The evidence is strongest when stated precisely. The EHT measured signals consistent with compact ring-like emission and a central depression at the expected horizon scale. General relativity supplies the interpretation connecting that structure to curved spacetime. The first famous target was the supermassive black hole at the center of the galaxy M87. Known as M87, it has a mass of roughly 6.5 billion suns. That enormous mass creates a correspondingly large horizon-scale region, making it a suitable target despite the galaxy's great distance. The reconstructed image revealed a bright ring surrounding a central brightness depression. The ring was not perfectly uniform. One part appeared brighter, as expected when moving plasma and curved light paths shape what reaches the observer. The dark center was identified with the black hole's shadow rather than a material black surface. The measured ring diameter was about 42 microarcseconds, with an uncertainty of roughly 3 microarcseconds. A microarcsecond is an angular measure so small that ordinary experience offers little intuition for it. What matters here is that the measured size could be compared with the scale predicted for a compact object having the independently estimated mass of M87. That comparison produced a major result. The ring scale was consistent with the horizon scale lensing structure expected from general relativity around a black hole of approximately that mass. The image did not merely present an attractive circle. Its measured angular size connected the observation to the geometry developed through decades of theory and modeling. Yet M87 represented only one kind of system, extremely massive, distant, and associated with a powerful large-scale jet. A second target offered a very different test, Sagittarius A. Located at the center of our own galaxy, has a mass of roughly 4 million suns. It is much less massive than M87, although it is also much closer to Earth. The balance of distance and size made the apparent horizon scale region of Sagittarius A accessible to the same global observing technique. But the source created another difficulty. Because the system is smaller, the plasma close to it changes much more rapidly during an observing session. The EHT was effectively trying to reconstruct a target whose visible emission pattern changed while the measurements were being gathered. An ordinary long exposure of a moving subject can blur changing details. The Sagittarius A challenge was more complex, but the broad problem is comparable. The reconstruction had to account for a source that did not remain visually fixed. Researchers therefore had to identify image features that persisted across many possible changing states. The resulting reconstruction again showed a bright ring surrounding a central brightness depression. The measured ring diameter was approximately 51.8 microarcseconds, with an uncertainty of about 2.3 microarcseconds. Its scale was consistent with expectations for a black hole of roughly 4 million solar masses. The two images do not look identical in every detail, nor should they. The masses, surroundings, timescales, plasma conditions, viewing geometries, and observational challenges differ. The important shared feature is the appearance of a ring and central shadow on the scale expected from strongly lensed emission around each compact object. This shared scale supports the underlying geometric picture. Light from surrounding plasma is bent around the central region. Some paths reach the observer and contribute to the ring. Other paths are captured, helping produce the central shadow. The observed diameter depends on the mass and geometry, rather than on an arbitrary vertical direction or the shape of a funnel illustration. The observations therefore give us evidence for the same near-horizon structure from two very different black holes. M87 contains billions of solar masses. Sagittarius A contains millions. One appears relatively steady during the observations, while the other changes rapidly. Yet both show horizon-scale emission consistent with the expected ring and shadow pattern. Still, careful language is essential. The EHT did not photograph a singularity. A singularity is part of the classical description of the deep interior and cannot send an image outward. The dark center of the reconstruction is not a visible dot showing where the singularity sits. The telescope did not photograph a solid event horizon surface either. The horizon has no material crust available to reflect or emit light like the surface of a star. The EHT detected radiation from plasma outside the horizon and reconstructed how that radiation appeared after traveling through the surrounding spacetime. Even the phrase "photograph of a black hole" is a useful shorthand rather than a complete technical description. What was measured was horizon-scale emission shaped by the presence of the black hole. The shadow provides evidence of captured light paths. The surrounding ring provides evidence of emission and strong lensing. Interpretation connects those measurements to the black hole model. This also means the results should not be turned into proof of every theoretical detail. Agreement with the predicted ring scale strongly supports the general relativistic picture in the observed region. It does not directly reveal every property of the horizon, settle every question about rotating geometry, or show what happens after matter crosses inward. Observation, reconstruction, and inference form a chain. The telescopes collect signals. The global data produce a constrained image. The measured features are compared with models. Confidence comes from the agreement among those stages, while scientific honesty requires that they not be collapsed into one claim of direct sight. For our question about direction, the EHT results deliver an important payoff. They do not show a funnel pointing below space. They show emission organized around a central shadow whose scale matches the curved light environment expected near black holes. The images support a surrounding geometry, not a downward opening. They also confirm why apparent position must be interpreted carefully. Brightness around the ring depends on moving plasma, viewing geometry, and the paths taken by light. The top of an image does not reveal an absolute top of the black hole. It is one orientation of reconstructed radiation reaching observers on Earth. The evidence carries us closer to the event horizon than ordinary vision ever could, but it also brings us to a strict boundary. Every signal in the reconstruction originated outside the horizon or followed a path that remained able to reach us. No pixel contains a message sent outward from the interior. The telescope can measure the environment where escape remains possible. It cannot look through the horizon as if the shadow were an open window. To ask what direction means after crossing that boundary, we have to leave direct observation behind and follow the predictions of classical space-time geometry. Every image and signal considered so far belongs to the exterior. Light reached the telescope because its path remained able to escape. Once the event horizon is crossed, that observational route closes. What follows cannot be described from direct messages sent back to us. It comes from extending classical general relativity into the black hole's interior. That distinction should remain visible throughout the discussion. The exterior geometry can be tested through the motion and light we observe. The classical interior is a prediction of the same theory, but no telescope outside can receive a report transmitted outward from within the horizon. We can follow the equations, yet we cannot compare the deepest region with a returning image. Crossing the horizon is not like striking a wall. The boundary contains no solid material. For a sufficiently large black hole, an infalling observer might cross without encountering one sudden local marker announcing the exact moment. The observer's immediate surroundings need not contain a glowing line, a crust, or the mouth of a tunnel. The absence of a local wall does not make the crossing unimportant. The horizon is defined by a global consequence. Before crossing, some future paths can still carry light, or an escaping traveler toward the distant universe. After crossing, every future directed path remains inside the black hole region. This separates the infalling observer's experience from the description used by someone far away. The distant observer receives signals affected as the infaller approaches the horizon, but no later signal returns from the interior. The infaller continues along a path and crosses the boundary. These viewpoints describe different information. They do not create two horizons or allow the traveler to report back. No change of orientation solves the problem. The observer can rotate the spacecraft so that its ceiling points inward or its engines face the direction once called outward. Cabin labels change, but the set of future paths does not. This is where the difference between local up and causal escape becomes decisive. A direction can remain meaningful locally while failing to lead toward the external universe. The horizon removes one possibility without erasing local space. The observer can still compare directions and watch objects move nearby. What has vanished is a route whose signals reach infinity. The last outward direction refers to causality, not to a compass needle losing orientation. An observer may still point a flashlight in what feels like an outward direction. The light leaves the flashlight and moves locally away from the observer, yet its future route cannot carry it through the horizon and onward to external infinity. Even outward-pointed light is trapped by the causal structure of the interior. This is more subtle than a force simply pulling the beam backward through space. The light always follows an allowed future path. Inside the horizon, however, the available future paths no longer include escape to the outside universe. The loss is not merely a shortage of speed. There is no faster direction that restores an outward future. The role of radial distance changes in that causal structure. Outside, decreasing radius and increasing radius can describe different possible motions. A traveler may move inward, turn engines outward, or choose another path if conditions allow. Inside the classical Schwarzschild horizon, moving toward smaller radius is bound to the traveler's future in a way that cannot be avoided by ordinary steering. This idea is sometimes compressed into the phrase that space and time exchange roles inside the horizon. Taken too literally, that phrase can create new confusion. The important meaning is that reaching smaller radius becomes inevitable for future-directed motion. It is not simply another location that can be avoided by turning left, right, up, or down. The classical Schwarzschild description ends at a singularity. It is tempting to place that singularity at the pointed bottom of the old funnel. But that image repeats the same mistake already removed. The singularity is not a hidden object sitting beneath the horizon in ordinary external space. In the classical interior, the singularity is a space-like future boundary. Every future-directed path taken by the infalling observer reaches it. Describing it as being in the observer's future is therefore more accurate than describing it as being downstairs. A restrained comparison can clarify the difference. An object located ahead on a road might be avoided by steering around it. A future moment cannot be avoided in the same spatial way. Turning the vehicle changes where the traveler goes, but it does not create a route that escapes having a future. Inside the classical Schwarzschild black hole, the singularity has this kind of unavoidable causal role. The comparison has limits. A singularity is not an ordinary moment on a clock, and the interior geometry is not daily experience stretched into a dramatic setting. The useful point is only that the destination is imposed by the structure of future paths, not by a universal downward direction. For the infalling observer, a finite amount of personal time remains after crossing. The exact experience depends on the black hole and the path taken, but classical general relativity does not provide an endless interior corridor. The future-directed journey terminates at the singularity predicted by the model. Rotation makes the mathematical interior more complicated. In the Kerr description, the classical singularity has the form of a ring rather than the Schwarzschild model's simpler singular boundary. The complete mathematical solution also contains regions that can encourage ideas about passages, other domains, or unusual routes through spacetime. Those possibilities must not be turned into observed geography. The ideal Kerr extension is a mathematical structure, not evidence that real rotating black holes contain stable, traversable wormholes. Real black holes form in changing astrophysical environments, and no signal from the interior has confirmed a passage to somewhere else. More fundamentally, the appearance of a singularity signals a limit of classical general relativity. Quantities in the classical description become extreme in a way that indicates the theory cannot supply a complete physical account there. The model successfully describes much of the exterior and predicts the causal boundary, but its singular endpoint should not be treated as the final microscopic picture of reality. A theory that includes quantum effects of gravity would be needed to describe what ultimately replaces or resolves that endpoint. No confirmed account is available in the supplied framework. The responsible conclusion is not that anything imaginable lies inside. It is that the classical prediction reaches a boundary where present knowledge remains incomplete. This changes the original idea of a bottom for the final time. Outside the horizon, no absolute downward direction exists. At the horizon, there is no solid rim. Inside, the singularity is not located underneath the black hole as a place in ordinary surrounding space. It lies in the unavoidable future of classical infall. The question of direction has become a question of causality. Above and below belong to chosen axes or surrounding structures. Inward and outward describe radial relationships outside. Beyond the horizon, outward no longer provides a future route back to the distant universe. We have now reached the limit of what each layer can tell us. Geometry explains the horizon. Rotation supplies poles and an equator. Matter creates disks and jets. Curved light rearranges their appearance. Telescopes test the exterior scale. Classical theory predicts the interior but ends at its own singular boundary. All that remains is to assemble those layers into one exact answer. What, in each physical case, is directly above and below a black hole? The answer to what lies above and below a black hole depends on which black hole we mean, which reference we choose, and whether we are describing physical structure or an observed image. Once those conditions are separated, the apparent mystery becomes a set of precise answers. Begin with an isolated, non-rotating Schwarzschild black hole. Remove the stars, glowing gas, magnetic fields, and every other external marker. The remaining horizon is spherically symmetric. No part of it is intrinsically the top. No opposite part is intrinsically the bottom. It has no spin axis, physical north pole, or preferred equatorial plane. An observer may still draw coordinates around it and name one direction north. Another observer may choose a different axis. Both systems can describe locations correctly, but neither label uncovers a physical difference in the ideal horizon. Rotate the entire arrangement, and the underlying geometry remains equivalent. For this first case, the direct answer is simple. Nothing distinctive lies absolutely above or below the black hole, because it has no intrinsic above or below. Every radial approach is equivalent after the complete system is rotated. A spacecraft arriving from the lower edge of a picture is not approaching an underside. It is approaching the same surrounding horizon from another direction. The answer depends on scale without changing its logic. A stellar mass horizon and a supermassive horizon differ enormously in size, while the same distinction between absolute orientation and relative structure remains. Mass changes the dimensions of the system. Spin, matter, fields, and viewing position determine which directional features become visible. Now allow the black hole to rotate. The Schwarzschild description gives way to Kerr geometry. Angular momentum selects a physical spin axis, producing two opposite polar directions and an equatorial region. Pole and equator are no longer interchangeable in every description. This makes a relative above and below meaningful. Observers can agree to call one pole above and the opposite pole below. Their words refer to measurable orientation relative to the black hole's spin. They have not discovered a universal vertical. Another black hole may rotate along another axis, and the names of the two poles can still be reversed without changing the system. For the rotating case, the answer becomes above and below can mean the two opposite directions along the spin axis. Around the middle lies the equatorial region. The distinction comes from angular momentum, not from the black hole being a pit with one open end. Next, place the rotating black hole inside an active astrophysical environment. Matter approaching it normally carries angular momentum. Much of that material settles into an orbiting accretion flow that can become concentrated around an equatorial plane. The visible disk is hot plasma outside the event horizon, not a surface of the black hole. Magnetic fields and rotation can also help produce opposing relativistic jets along the polar directions. In a suitable active system, an observer may therefore find a jet above one spin pole and another jet below the opposite pole, with orbiting plasma around the equatorial region. This is the strongest visible answer to the title, but it is conditional. Not every black hole has a bright disk. Not every rotating black hole launches an observable jet. Accretion flows change, and jets can weaken, become uneven, or disappear. The horizon and spin axis may remain even when surrounding structures become faint. The jets also do not emerge from inside the black hole. Their launching processes operate in the external magnetized environment, where energy and signals can still travel outward. Nothing crosses inward through the event horizon, reaches the singularity, and then escapes back through a polar opening. A jet is evidence of activity around the black hole, not a leak through its causal boundary. For an active system, then, above and below may physically contain polar outflows, while the equatorial region may contain orbiting plasma. These structures reveal the black hole's relative orientation, but they belong to its changing surroundings rather than defining the horizon itself. Now consider the image received by a distant observer. Even after the disk and jets are located physically, their light does not travel through ordinary flat geometry. Near the black hole, space-time bends the routes followed by that light. Emission from the far side of the disk can curve around the central region and reach the observer. Light from the underside can be bent upward and appear above the shadow. The disk may consequently look as if it wraps around the central darkness, even though the plasma remains concentrated around an equatorial flow. This means an image has its own answer to the title. What appears above the shadow may include light that began below or behind the black hole. Apparent upper and lower positions record the final arrival directions of curved light paths. They do not provide a direct map of the original locations of the emitting matter. The bright ring in such an image is not a solid horizon. It is external emission shaped by plasma motion and gravitational lensing. The central shadow is not a picture of the singularity. It is an apparent dark region shaped by paths that fail to deliver surrounding light to the observer. The Event Horizon Telescope observations of M87 and Sagittarius A support this horizon-scale ring and shadow picture. Their reconstructed emission appears on the characteristic scale expected for their independently constrained masses. The evidence supports strongly curved exterior geometry. It does not transform the image into a view through the horizon. At the event horizon itself, the answer changes from orientation to causality. The horizon surrounds the black hole region. It is not a mouth at the top of a funnel, and it has no solid underside. From outside, an observer can approach it from any available physical direction. Crossing inward closes every future route that could return a signal to the distant universe. Inside, the old language of a bottom becomes even more misleading. In the classical Schwarzschild description, the singularity is not located below the horizon in surrounding external space. It is a future space-like boundary, reached by future-directed infalling paths. Avoiding it is not a matter of steering around a lower object. For a rotating Kerr black hole, the classical singularity has a ring form and the mathematical interior is more complicated. But this does not provide observational evidence of a hidden lower chamber or traversable passage. The description remains a classical model of a region unable to send its own confirming message outward. We can therefore assemble the entire answer in one sequence. A non-rotating black hole has no preferred above or below. A rotating black hole has relative poles and an equator defined by spin. An active rotating system may place jets along the poles and a disk around the equator. Curved light can move emission from physical below into apparent above. The horizon surrounds rather than opens downward. The classical singularity lies in an infaller's future rather than underneath space. Each statement belongs to a different layer. Spherical symmetry and rotating exterior geometry are features of the physical models strongly supported by observation. Disks, jets, and radiation are observable but changing environmental structures. Image positions are produced through curved light paths. The singular interior is a classical prediction beyond direct external observation. Keeping those layers separate prevents one picture from answering every question incorrectly. The embedding funnel cannot locate the underside. The glowing disk cannot be mistaken for the horizon. The jets cannot be treated as escape tunnels. The shadow cannot be treated as a photograph of the singularity. The direct answer is therefore not that nothing exists around a black hole. Many real structures may be present. The answer is that above and below have meaning only after a reference is defined. For an isolated non-rotating black hole, no preferred reference exists. For a rotating one, spin supplies it. For an active one, matter and fields can make it visible. What remains uncertain lies deeper than the original directional puzzle. Classical general relativity reaches a singular endpoint, while the physical quantum structure that replaces or resolves it is unknown. Some details of how plasma and magnetic fields maintain powerful jets also remain under active investigation. These uncertainties do not restore the funnel or create an absolute bottom. The governing question is now resolved. There is no universal region directly above or below a black hole. There are radial directions, spin-relative poles, equatorial flows, conditional jets, lensed images, a causal horizon, and a classical interior whose final nature remains incomplete. The last question is why the false picture felt so natural in the first place, and what its failure reveals about the limits of the spatial intuition we carry into the universe. The false funnel has now been replaced by a more reliable picture. Black holes sit at a boundary between physics that has been tested with precision and questions that our present theories cannot answer completely. Outside the horizon, the foundation is strong. A non-rotating black hole is described with spherical symmetry. A rotating black hole provides a spin axis, relative poles, and an equatorial region. Matter can form an accretion flow around that region, while suitable magnetic conditions can help produce polar jets. Light bends through the surrounding geometry, and horizon-scale observations reveal the ring and shadow structure expected from that environment. Accretion flows, jets, moving plasma, and lensed emission can be observed. Their interpretation uses physical models, but signals from the exterior remain available for comparison. Measurements can improve, models can be challenged, and predictions can be tested against new data. The event horizon marks where that direct exchange changes. We observe its effects through matter and light outside it, but we cannot receive a message sent outward from the interior. Classical general relativity still provides a description beyond the horizon. It predicts the causal path toward a singularity and gives different mathematical forms for non-rotating and rotating interiors. Yet a classical prediction is not the same as direct observation. The singularity shows where the theory reaches an extreme endpoint rather than supplying a complete final account of nature. Describing that endpoint as a point or ring within a classical solution does not tell us what a successful quantum theory of gravity would ultimately reveal. That deeper structure remains unknown. We do not know what physically replaces or resolves the classical singularity. We do not have an observation from the interior that can choose among proposed possibilities. The responsible boundary is therefore clear. Exterior geometry is strongly supported, the classical interior is model-dependent, and the quantum description remains unresolved. Uncertainty does not mean every imagined answer becomes equally plausible. A lack of confirmed quantum structure does not turn wormholes, hidden worlds, or escape passages into established facts. Any successful explanation must still account for the exterior physics that has already survived observation. The unknown begins where evidence and current theory end. It is not permission to erase everything known before that boundary. There are smaller uncertainties in the visible environment as well. The broad relationship among black hole spin, magnetized accretion, and powerful jets is supported, while detailed plasma behavior remains an active problem. Better observations and models can refine how energy is transferred and how jets remain organized. That uncertainty concerns the mechanism's finer structure, not whether every jet emerges from a singularity. The distinction between levels of knowledge is what allows wonder to survive without becoming exaggeration. We can be confident that the funnel's vertical is artificial. We can be confident that a non-rotating horizon has no preferred side. We can identify spin-relative poles in a rotating system, and we can still admit that the final interior lies beyond a complete present description. Why, then, did the idea of a bottom feel so convincing? Human spatial intuition is built from ordinary surroundings. We live where gravity is weak compared with the region near a black hole and where space is close enough to flat for daily movement. Objects fall toward the ground. Holes open through surfaces. Above and below are reinforced by every step we take. In that environment, the words require almost no explanation. Down points toward the ground. Up points away from it. A hole has an opening, walls, and a lower region. When something falls in, we imagine it moving from one side of a surface to another. These expectations are useful because they describe the scale on which human life takes place. The mistake begins only when those expectations are carried into a system with a different geometry and treated as universal rules. A black hole is not an ordinary hole enlarged to cosmic size. Its event horizon is a causal boundary, not a broken surface. Its exterior can surround the hidden region in every radial direction. Rotation can define an axis, but no axis becomes the universe's permanent vertical. Our intuition did not fail because it was foolish. It reached the edge of the environment that trained it. The same mind that expects a floor beneath every hole can also build instruments, mathematical models, and global telescopes that reveal why the expectation fails. Science does not require us to begin without intuition. It requires us to revise intuition when evidence demands it. This is why representations matter. The funnel was created to make an unfamiliar geometric relationship visible. It reduced dimensions and added a direction that our eyes could understand. Used within its limits, it can still help communicate that the space around a black hole is not behaving like an ordinary flat grid. The trouble begins when the aid becomes the object. The added depth becomes a physical pit. The slope becomes a route. The narrow end becomes a bottom. A choice made for the viewer's benefit becomes a claim about the universe. The image has then stopped simplifying one relationship and started inventing another. Knowing this does not require us to discard the funnel from every explanation. It requires us to read it with care. We can see the bending grid and remember that its vertical dimension displays selected geometry. We can use its shape to begin a question while refusing to treat its underside as a destination. The transformed image carries a wider lesson. Scientific models are powerful, not because they reproduce reality in every detail, but because they preserve relationships that matter for particular questions. Their boundaries are part of their meaning. A model becomes more useful, not less, when we know exactly where its literal interpretation must stop. Black holes make that lesson unusually visible. The closer the investigation moves toward the horizon, the more carefully ordinary words must be handled. Surface, ring, shadow, inward, above, below, and future can each describe something useful, but only when the reference and evidence behind them remain clear. The original question therefore led somewhere more interesting than the underside of a cosmic pit. It revealed how direction is created through symmetry, motion, matter, observation, and causality. It showed that correcting a familiar image does not remove mystery. It replaces a false mystery with a real frontier. Return now to the opening picture. The flat grid sinking into darkness, the steep walls narrowing toward an unseen depth. The image can remain, but its meaning has changed. There is no spacecraft waiting beneath the sheet, no hidden floor below the horizon, and no universal down into which the black hole points. The funnel was never a view from outside the universe. It was a bridge between unfamiliar geometry and familiar human sight. Its downward direction was never a property of the black hole. It was the direction from which we first tried to understand it.